Okay, so we want to prove for propositions P and Q that the negation of P implies Q is logically equivalent to P and not Q. The reason why we want to show this logical equivalence is because this is useful to us for proof by contradiction in the future. So let's go ahead and start this proof. Okay, so we're going to do this by truth table. So we're going to do P, Q, and then we need all the possible combinations between P and Q. We can do that through this scheme here. So true, true, false, false, and true, false, true, false. Notice how we get all the possible combinations between P and Q, where P can either be true or false, and Q can either be true or false. Right, true, 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 false, false, true, and false, false. The next thing we need to do is get this inside part here. P implies Q, right? So we have true implies true. We can have a true assumption lead to a true conclusion. What we can have, however, is a true assumption lead to a false conclusion. So that will be false. You can have a false assumption lead to a true conclusion for sure. So that'll be true. And you can have a false assumption lead to a false conclusion. So that is true as well. Okay. So the only time P implies Q is false is when you have a true implies false. So now let's go ahead and do the negation of P implies Q. Okay. So that will be, let's see, the negation is just the opposite of P implies Q. So that'll be false, true, false, false. Now for P and not Q, we need the not Q first. So not Q. So not Q is just opposite of Q. So that'll be false, true, false, true. And now we can do P and not Q, right? So P and not Q. So and means both of these need to be true in order for this whole thing to be true. So we have true and false, which is false. True and true, which is true. False and false, which is false. False and true, which is false. So notice, scooch down a little bit here. Notice that this, the not P implies Q column, and the P and not Q column have the same outputs, right? For the respective rows. We have FF, TT, FF, FF. So what this tells us is that the negation of P implies Q is logically equivalent to P and not Q, which is what we wanted to show right up here. Okay, so that is the proof.